Okay. Wait, I mean, just let me do a small correction. I mean, it's a correction. It's not, what I said is not very wrong, but you know. Like S being T set. We say that the action of G on S is transitive. I didn't write that, so please write this. If there is only one orbit, which is S. Okay? I wrote if S is the only orbit, right? That's what I wrote. It's not wrong, but it's better. This one is better. Okay? It's good. I see the class filling up again, so it's okay, great. By the way, what do you prefer for the final exam? Office hours or review session? Extra office hours or review sessions? Okay. Okay. I mean, I'll have two or three more office hours, but if I don't have a review session, I can have 4 or 5 office hours. Okay, so I'll do a review session. I'll do maybe two review sessions. Okay. So we were talking about P groups last time. Okay, now I'll modify the statement that we did. So proposition, let G be a P group. So G is equal P to the K for some K in N. Of course, P is a prime number. Then if I belongs to 0, 1 up to K, G has a normal. Last time I didn't put, I think the honors section will do it with normal, so let's do it with normal. I mean, it's not that bad. Subgroup of order e to the f. Okay? And the proof of that is by induction. We started the proof, right? We started the proof of that. I didn't put normal, if you remember. Did I do that? Yeah. Prove that. The proof of that is by induction. By induction on K. So if K is 1, and the size of G is P, then EG and G are the only normal subgroups. In fact, they're the only subgroups. Okay, great. This is the base case, right? The base case holds. I have proved that I have a normal subgroup of size p to the 0 and a normal subgroup of size p to the 1, right? Okay, now induction. Now a lot of you ask why did I not do examples with induction? There it is. Okay, we'll do more induction today. So suppose the result holds for groups, or P groups of size P to the K minus 1, and let G be a group of size P to the K. I'm repeating the argument, I'm rewriting the argument because it's important. And let G be a group of size P to the K. We will show that the statement holds if G has size P to the K. Now, What do I know about a P group? What do I know about its center? The center of a P group, what can I say about it? If G is a P, yeah? It's great, exactly. It's divisible by P, very good, yeah. So we know from homework 4 that ZG has size P to the alpha, or some alpha in N. Hence, P divides ZG. You see why I didn't say bigger equal? Because I just wanted this statement. But P divides ZG, hence by Cauchy. Is this thing recording? This thing? Yeah, okay. Hence by Cauchy's theorem, ZG as an element X of order P. Okay? Now let H be the subgroup generated by X. We showed last time that H is a normal subgroup of G. I'll show this again. The center has that property that every subgroup of the center is a normal subgroup. That's not true in general. It's not true that every subgroup of a normal subgroup is normal, but this is true for the center. We'll see why. Let Y belongs to X, which is in ZG, and G in G. Then GY, G inverse. Now Y is in the center, so Y commutes with everything. So this is just Y, G, G inverse, which is just Y, which belongs to X. Right? This is where we reached last time. No? Remember that? This is where we reached last time. Now, if I have a normal subgroup, and I have a group, what can I do? I can construct a new group by taking what? Yeah, but what do we call the group? Very good. The quotient group. Okay? So G mod H is a group of size, G has size P to the K, and H has size P, so this has size P to the K minus 1. Group of order P to the K minus 1. So far so good. Following? Are we following? Yeah. G mod H, what is the size of H? Look at H is the cyclic group generated by X. What is the order of X? P. So the H has size P. G mod H, what is the size of G? Yeah? Divided by the size of H, what is that?
Where do we get that formula?
This is just this, right? The number of left cosets.
Oh, right, yeah.
Okay? Okay. Now let phi H from G to G mod H denote the projection. I mean, I've used the projection before, right? Projection G to G mod. Use the coset GH. In the book they call it canonical. So let's not use it. Let's not use the word canonical. But you know. Now I want to apply the induction hypothesis to P to the K. To P to the K minus 1, right? I can apply the induction hypothesis to P to the K minus 1. I can apply this, the induction hypothesis, to G mod H. What is the induction hypothesis? That I have a normal subgroup of each possible power of P that is less than K minus 1. Yes. Agree? Everybody, read your notes. The induction hypothesis says that this is, I can find a subgroup, a normal subgroup of size p to the I for each I less or equal than k minus 1. Did you read your notes? Yeah, you read them? Okay. By induction hypothesis, if I belongs to 0, 1, k minus 1, there exists a normal subgroup of H, of G mod H, a normal subgroup, let's call it H tilde, say, of size P to the I. Now, your current homework, pi inverse of H tilde is a subgroup of G. You can show it's a normal subgroup. You can show it's a subgroup. In this homework, you have to show it's a subgroup, right? And you can show that if H tilde is normal, then pi H inverse H tilde is normal. Okay? It's not complicated. It's 2 lines.
Wait, is that from the bonus one?
Yeah.
Okay.
Homework 7.
No, the extra one. Yeah. And the first question, right? Isn't that you have to show pi inverse of H is a subgroup, and the size of pi inverse of H?
Question
No.
3?
I don't remember. I can't remember.
Yeah, it's one of them. It's when n is normal, the inverse
Exactly.
of phi is normal and g is a normal subgroup.
Yeah, so I don't remember it, but I remember that this is the result. That pi inverse of H tilde has size,
N times
the size of X, very good, times the size of H tilde, right? N is here, right? Agree? This is if you want, this is the size of H. If you want to keep the notation like the homework, H is here. Tuck, tuck, right? That's it, right? Yeah? What is the size of H? It's P. And H tilde is P to the I, so this is P to the I plus 1. Hence, hence what? Hence what? Hence, if I belongs to 0, 1, up to k minus 1, G has a normal subgroup of size p to the I plus 1, hence G, well, has, well, so if I ranges in 0, 1, k minus 1, what are the sizes of the normal subgroups of G that you get from here? You get size p squared, size p cubed, size p to the k. Hence, G has normal subgroups of size p squared, p to the k, and of size 1, namely the identity. And of size p to the k is just G, right? The normal subgroup of size p to the k is just G. So, and this proves the clue. I don't know what you do in general, like do something like that? I don't know what. Yeah. So the converse of Lagrange's theorem holds for B groups. And not only can you find the subgroup that for each divisor of p to the k, but you can make that subgroup normal. Which is pretty cool, I guess. Okay? Any questions? No questions? Great. Now we'll go back to group actions. We'll go back to group actions. And of course we'll relate this to P groups. Definition. The GBA group and S a G set define SG to be the subset of S such that G star S is equal to S for all G and G. We say that an element S0 in S is a fixed point of the action G on S. Why do I call it fixed point? Because G star S is equal to S for all G. Right? When you hit it by G, it doesn't change. Okay? This is definition. This is a subset of S such that G star so an element S0 is in S if and only if G star S0 is equal to S0 for all G and G. Okay, so it's a fixed point. Think of the center. The center is an element in the center is fixed under conjugation, right? Take G inverse, the action of G on itself by conjugation. What is the set of fixed point of this action? It's the center, right? Yeah, you see that? I mean, let's write this. Example. Consider G acting on G by conjugation. So you send Gx to G star x, which is Gx G inverse. What is that? So what is the, well, I mean, really this is this. I mean, it's a bad notation, but you know, G, right? SG, anyways. It's just the set x in G such that G star x is equal to x for all G in G. What is that? This is just x in G such that Gx G inverse is equal to x for all G in G. What is that? This is just the set x in G such that Gx is equal to xg for all G in G. And this is what? This is just zg. Right? Are we good? Following? Yes?
Is it element S0 in S or in SG?
In SG, thank you very much. Thank you. Oh no, we said that an element S0 in SG. Yeah, okay. Yeah, thank you. Yeah, thanks. Okay? In other words, S sub G is the set of singleton orbits, right? It's the union of singleton orbits, right? An element is a fixed point if and only if its orbit is a singleton. You see that? Let's prove that. Well, let's see that. So, S0 belongs to SG if and only if the orbit of S0 is S0. Well, what does it mean? Let's prove this. I mean, it's a one-liner. Prove. S0 belongs to SG. If and only if what? What is the definition of FG? It means that G star S0 is equal to S0 for all G in G, right? Read your notes. Read.
Orbit of SG.
Orbit of S0.
Zero.
S0 belongs to SG if and only if orbit of S0 is equal to S0. What is the definition of SG? Is the set of all S such that G star S is equal to S for all G and G. Right? Did we read that? Yeah, everybody? Did you read your notes? Read like 2 lines before. Okay, so S0 belongs to SG if and only if G star S0 is equal to S0 for all G and G. This is by definition. Now what is the set G star S0 as G ranges in G? This is the orbit, right? If and only if the orbit of F0 is equal to S0. Other words, SG is the union of singleton orbits. Okay, now let's prove one more theorem. I think I'll leave it to you as a homework exercise. But it's a pretty important one. It generalizes the whole importance of P groups. Theorem. Let G be a P group. When I say P group, P is always prime, okay? P is always prime. Let G be a P group, and so I defined P groups to be finite, or did I say finite P groups? Did I use the word finite P groups, or did I just say P group? P group. Okay, so I said a finite group is called a P group, right? I didn't give it a, okay. So P groups for now are finite, okay? In this class, P groups are finite, okay? So let G be a P group and S a finite G set.
You said a finite group G is said to be a P group.
Okay, so I define it only for finite groups.
Yes.
Okay, very good. Thank you. So let G be a P group and S a finite G set. Then S is congruent to SG mod P. If you think of it, this is what we've been using all the time. I decompose S into the union of singleton orbits and the union of non-singleton orbits. Now, the non-singleton orbits have size P, P squared, P cubed, and so on. When I reduce mod P, I get S on this side and SG on the other side. Okay? So write down the orbits, singleton orbits and non-singleton orbits, and show that the size of non-singleton orbits have size divisible by P, and reduce mod P. Okay? This is how you do it. Is it clear? So left as proof is homework. Okay, I mean, I'm telling you how to do it. In case you can watch the. I mean, there is someone who has actually told me, like, for the questions that I posted on the homework, that they went the one with the subgroup of index 2. They went and rewatched the lectures and saw how to do it. If you tried that question, did you try it? And if you have a subgroup, if you have a group of order 2k where k is odd. Yeah. Someone told me, like, they just rewatched the lectures and they just followed the steps. I mean, I said it very fast. Anyways, I mean, I said I would do it in the lectures, right?
Kinda.
Yeah.
Like
And then someone rewatched the lectures and then he told me that he got it from there. So that's good. So you can rewatch the lectures to get if you want to see this, how it's done, or if you want a hint. Okay. Enough with P groups. We'll generalize now. Okay, are we good with P groups? Are we good with this? You're going to have some homework. I'll post some homework on P groups next homework. Post some questions on P groups. Okay, any questions? Yes, sir.
This is like homework.
Homework, the next homework. What, I don't know, I lost count.
Homework.
Like the one that's not out.
Not today. Not this week. The other week. Next week. Okay? But is it clear how to do this? Like the center. Like the class equation. S is a union of orbits. Divide the orbits into orbits of size 1 and orbits of size bigger than 1. Any orbit of size bigger than 1 by the orbit stabilizer must divide the size of G. So any orbit of size bigger than 1 must be P, must have size P or P squared or P cubed or blah blah blah, right? Now when you add them up, the orbits of size bigger than 1 have size divisible by P when you sum them up. So when you reduce multi, it gets to 0. S stays S and SG stays SG. Okay? Write it down, it will be clear. Yes, sir.
So we have to rewrite well what we already did in class about proving that the orbits and multi-local orbits, we did the same thing as in the theorem before.
Exactly, it's the same idea. Exactly, exactly. Well, you don't have to. No, you don't have to reprove everything. You can just prove the orbit stabilizer here, right? You can just use it now.
We can use what you told us.
Exactly. Yeah, yeah. You can use everything we proved in class. Yeah. You know, S is a disjoint union of orbits that you know. You compose orbit of size 1, orbit of size bigger than 1, and you show that the size of an orbit of size strictly bigger than 1 is divisible by P. Okay? Using the orbit stabilizer. Great. Now we move on to an important theorem. Well, I will not. Now you know we've been interested so far in a converse of Lagrange's theorem. Whenever I have if I have a group of size, right? If M is a divisor of N, I know that I don't necessarily know that I have a subgroup of order M, right? I don't know that necessarily. I know it for cyclic groups. It turns out for finite abelian groups, this theorem holds. If you have an abelian group of order 16, then you must have a subgroup of order 4. And now we'll prove this. Very nice proof. Also, do you see what I mean? So if you have an abelian group of size 28, then you must have a subgroup of size 40, which is a strong result. We know it for cyclic groups. We know that if G is a group of size of size 25, then you must have a subgroup of size 5. That's Cauchy's theorem. Right? You have an element of order 5 because 5 is a prime dividing G, and hence you must have a subgroup of order 5. So now we'll try to classify more, try to find more subgroups of a group of finite groups G. Okay? This is really the last topic of today and tomorrow. And then we finish with groups. Okay? We'll start with rings, but groups will carry over with us, so we'll just keep it. We will need groups in our rings. Okay? So let G be a finite group. And P be a prime number. Suppose that G has size P to the k times M, where k belongs to n union 0 and GCD MP is 1. Then G has a subgroup of order P to the k. So in a subgroup of order 24, write down the prime factorization of 24. You have 2 cubed times 3. Okay? Yes, sir.
So what does it say after PK?
P to
PK.
times M. Here? M. Where K is belong to N union 0 and GCD MP is 1. Now, what does this mean? What does this imply? Say you have a subgroup of order 24. What is the maximal power of 2 that you have in 24? 3. So you have a subgroup of order 2 to the cube in 24. Pretty strong result. Yes, sir.
But if the GCD of M and P isn't 1,
Yeah,
then it just means that like N is divisible by P.
exactly. So you're just writing the prime factorization. You're extracting. Okay.
Yeah, but does that like in 24, can you, like, can we say that you must have?
Excellent question. Look at the previous part. Look at the previous part. So in a group of order 8, you have a subgroup of order 4 by the previous part of
Yeah,
P group.
this is what I mean. Like, we can find every
Exactly.
single one.
For every single prime number, you can find a subgroup of order 2 squared. 2. Very good. That was the next part. But yeah, you guys see what he's saying? So if I have a subgroup of order 2 cubed, then by the previous theorem on P groups, I have a subgroup of order 2 squared. Because in a P group, you have a subgroup of every possible order dividing the size of the group. You guys see that? Yeah? Read the previous theorem, and that's what you get. Yeah, every subgroup of a subgroup is a subgroup. Yeah. It's not necessarily normal, but it's a subgroup.
So we can have like any power of
Exactly.
any prime. That we-
Exactly. The question is that this is resolved now. The question is that one is I have a subgroup of order 2 and a subgroup of order 3. What do I get when I join them together? Right? Very good question. Yeah, very good. Very good. Okay, let's prove this. How are we going to do that? By induction. Yay. Proof. Induction on the size of G. Well, if G has size 1, then you can write G as P to the 0 times 1, right? P to the K, where K belongs to n union 0 times 1. So EG is a subgroup of G, well, really is equal to G of order P to the 0. Now, this is by strong induction. Suppose that that the statement is true. That G is a group of size P to the K times M, where K belongs to n union 0, and GCD empty is 1. And that the statement is true for all groups of size strictly smaller than G. By the way, this proof you're not responsible of for the final. Okay, I will not ask you to do this proof. Okay, I might ask you parts of it. If I need to ask it to you, I will give you the steps. Okay, I'll tell you, do this, do this, do this, and do this. Okay, I'll not tell you prove this theorem. Now, let's divide two cases. One, the silly case is that if P does not divide G, then K is equal to 0. Agree? If G has size P to the K times M, and P does not divide G, then K is 0. Agree with or not?
Yes.
Right? Then G has a subgroup. Then EG is a subgroup of G of order P to the 0. Definitely this is not the interesting case. The interesting case is when P divides G. We agree? Yeah? Everybody? We agree? Now if P divides G, I need more space for this one. It's the same argument as for P groups, but we'll have to modify it a bit. It's the same, it's really the same argument. If P P divides G, what can I do?
That's a group of size.
Ah, very good. Very good. We're gonna use that. Now, the thing. So you said that you need a group of size P, right? Because by Cauchy's theorem, right? Yeah. Now we need this group to be normal, the subgroup to be normal in order to take a quotient. In general, there is no guarantee that this subgroup is normal. So now we'll try to make it normal. Okay? Technique. This is the idea of the group. Plus sum I equal k to n g cxi, right? Where cxi is the set of g and g that commute with x. Well, cx commute with x. I don't know if I ever called this group. We call it the centralizer of x.
Never gave us the name.
I never called it. We call it the centralizer of x. Okay. Centralizer. Anyways, it's a name. Just like I'm called Majid, it's called centralizer. Okay. I mean, there are reasons for both, but anyways. Centralizer of x. And what are x and what are oh man, did I use xk? Let's use L. Well, I don't want to use L. What? I equal m, right? Because k appeared here. Like, where?
But you already used M.
Did I use m or O? Man, running out. N.
J.
Oh, yeah.
J is bad because J is usually an index. Let's use A. Unusual. And xa plus 1 up to xn are representatives of non-singleton conjugacy classes. Right? We remember this from homework 4, right? Remember we derived this in homework 4. This is what we're going to play with now. This is what we're playing with to find the to use the induction hypothesis. Okay. One more chalk. Guess integrals take up a lot of chalks. There's. We have integrals, and then before that there is a course on calculus. So all of them use boards. So if non-singleton conjugacy classes. Great. Now let's. So if G were, what did we usually do here? We said that this stuff is in homework 4. We said that this is divisible by P, and this is divisible by P. So ZG must be divisible by P.
Yes.
Now I cannot do that unless I make extra assumptions. Right? Because G is not a prime power order. But we can relate. Well, we can reduce. Well, not reduce. I don't want to say reduce it, but we can try to resort to the same kind of argument if we make some assumptions. So I have if P divides G, blah 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 blah. Now assume that P does not divide the index of C xi0 for some I0 in A up to A. Okay? Assume that P does not divide one of these. Okay? So how many powers of P do I have in the prime factorization of this? 0, right? If P doesn't divide this, Cxi0, how many powers of P do I have? Everybody? 0, right? How many powers of P do you have in a number that's not divisible by P?
0.
0. Now if I write G, I can do that, right? You guys can see this? This is just the cosets. Index times the size of the group is the size. Index times the size of the subgroup is the size of the group. Isn't that right? Everyone? Yeah? We're following? Now what is the power of P that divides G? What is the size of G? P to the k times m, where m is co-prime to P. What is the maximal power of P that divides G? G is P to the k times n. So it is k, right? So here I know that P to the k divides G, right? G is P to the k times n. I mean, we'll try this. Now, what is the maximal power of that divides this if P doesn't divide? 0. So what is the maximal power of P that divides this? K. Hence, okay, we see the argument here? Everybody, we see the argument? Okay, I know that P to the k divides G. Agree? This is the largest power of P that divides G. I know that P doesn't divide this. So how many P's do you have in the prime factorization of this one? 0. So how many P's must you have in this one? K. Okay? So P to the k divides Cxi0, and hence, of course, you cannot have any other power of k dividing, any higher power of P dividing Cxi0. Cxi0 is equal to P to the k times, did I use L?
You use m in front, but inside you use l.
Where?
Which one are you trying to use?
Where did I use L?
No, I don't
Never.
think so.
Never, okay. I mean, you can say it in a better way, okay?
Sorry.
Yeah? Okay, so P to the k times L. Okay? Where L
It kind of looks like a D.
looks like any. Suits Z, well, no, Z.
Make it taller?
L,
Yeah.
P to the k times L, where just the D. Now I claim that P to the k times L is strictly less than the order of G. That this L can be equal to M. I know that Cxi0 is the size of a non-singleton conjugacy class, right? So if it's a non-singleton conjugacy class, what is the size of it? Can it be equal to 1? If the conjugacy class, this is equal to the conjugacy class of Xi0. Right? Orbit stabilizer, or homework 4, whichever you want to use. Now, this is a non-singleton conjugacy class, so what is the size of this? Can it be equal to 1? This is strictly bigger than 1. Hence, Cxi0 has size strictly less than G. If the index is strictly bigger than 1, then Cxi0 has size strictly less than G. Therefore, I can apply the induction hypothesis to Cxi0. Hence, my induction hypothesis, hence my induction hypothesis, Cxi0 as a subgroup of size d to the k. So G as a subgroup of size d to the k. Very good. Huh? That's nice. That's a nice argument. Now, am I done? I made an assumption that P divides the index of Cxi0 for some I0. This is a strong assumption. What if P doesn't divide any of these? Sorry, I made the assumption that P does not divide this index for some I0, right? This is the assumption I made. Now, what if it's the case that P divides all of them? Then I can go back to my P group argument. Let's see how. Okay, so this is the first, let me draw right here. So if P divides G, you have two cases. P doesn't divide G Cxi0 for some I0, and then P divides Cxi for all I, right? These are the two cases. One or the other will hold. How much time do I have left? 10 minutes? 6. Okay, we'll finish it. We'll finish it. We'll finish it. G has subgroup of size P to the K. P divides G. Yeah. Okay. Now, suppose that P divides G Cxi for all I. You agree that these are the two cases. So if P divides all of them, or P doesn't divide one of them, right? Those are, you can break this up into two cases. If this one or this one. You see, you've seen this? If A, then not A is the other one. If P divides, P dividing all of them, what's the negation of that statement? P doesn't divide at least one of them, right? Yeah? So, sorry, so P divides. Oh, here it's. Yes.
That was
it.
it.
Okay.
That was it.
So P divides this one. If it divides all of them, then it divides the sum. Agree or not? Everybody, do we agree?
Yeah.
Now I know that G is equal to ZG plus this sum. And we're back to the P group argument. But you see that? This is divisible by P. This is divisible by P. So ZG must be divisible by P. We see that? Hence, ZG is divisible by P. We know that ZG has at least one element, so it has at least P elements, right? So ZG has a subgroup or has an element X of order D, and it's the same argument as of order P by Cauchy. It's the same argument as before. Since X is a subgroup of ZG, then X is normal in G by literally the same argument. And G modulo X, well, then H, let's call this, then G modulo H. Sorry if I just take 2 more minutes after the bell. I just want to finish this and not get back to it. Is a group of order. What's the order of G? G has P to the K times M. What's the order of X? P, yeah? No, say out loud. P. P, right, exactly. So what is the order of G mod H? Of size, of order? p to the k minus 1 times n. Agree? I can apply the induction hypothesis here because it has size. By induction hypothesis, G mod H as a subgroup H tilde of order e to the k minus 1. Hence, pi inverse, where pi is a projection, is a subgroup of G of order. What is that? 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 Of order H tilde times H, which is p to the k minus 1 times p, which is p to the k. Finito. Okay? Sharp. Well calculated. I mean, I still take the one out. Okay? Great. So this stuff is important.